Hello and welcome back to High Peak Education. At this point I would like to perform an intuition video which shows you about inductors. Now what is an inductor? I will discuss that more in later videos in terms of its applications, but an inductor is something that uses changing current through the inductor will induce a changing magnetic field through the inductor. And when I say changing, I mean changing in time. So if the electric current changes in time, the magnetic field changes in time, and the inductor can do several things. A lot of people think of an inductor as basically a device that sort of pushes back, if you will. And we'll see why that's not exactly right, but we will see that there's some truth to thinking about it that way. So let's imagine that we have an inductor, a resistor, an EMF source, and a switch. That is, this is a battery, which we can set the voltage of. This device here is a resistor, could be a light bulb, toaster, whatever. Now this inductor is, again, a special device. I'll only be showing single inductors in series with these other devices. I won't be showing several inductors in series or several inductors in parallel. And then this switch is also shown in this schematic diagram. Now this is the schematic diagram. Notice that these are the symbols you would draw if you were drawing a circuit diagram. If you wanted this to look more lifelike, you would note that a battery looks like so, a switch looks like so, and then notice a resistor has these colored bands on them depending upon how much resistance there is. And then here's an inductor. Now, by the way, this inductor, do you see that it looks like a lot of copper wire wound very tightly around in a cylindrical pattern? Okay. That cylindrical pattern it's wrapped around, it's actually a very tightly wound helix. And again, that's very similar to what you saw for the symbol we often use for an inductor. Now, an inductor most often has this shape. That's what we often call a solenoid. And a solenoid, again, has a very tightly wound helix for that copper wire or whatever the conductor is. So, the idea is that we are going to set this up, and we're also going to, instead of just showing you bare exposed wire, let's also show the electrons. So keep in mind, those electrons are meant to represent sort of what's going on in the circuit. What we have here on the upper left is we're showing the voltage difference across this resistor as a function of time. We're also going to measure the voltage across this inductor as a function of time with this voltmeter. We're going to keep track of the current in the circuit. And I believe the current in the circuit should be constant for all devices because everything is in series. And then we're also going to show you here the current in a graph that is current as a function of time. Okay, so we're going to plot these things after we close the switch. Now, by the way, this we call an LR circuit. That is inductor and resistor. Okay, so notice that we're going to have an inductor which is often given the symbol L for inductance, and a resistor which is often given the symbol R. And this is a voltage source. So we're going to let the voltage source here be 12 volts, and let's assume it's an ideal battery. Let's also assume that the resistance here is 10 ohms, and that the inductance is 50 henries. Now, henries is going to be the units for inductance. And again, inductance is often given the symbol capital L. Now, what we're going to do is we're going to close the switch here in a moment. So we're going to close the switch here. We're going to allow charge to flow, and we're going to see what happens. So notice what's happening. Notice that electric current is moving. Remember, these are electrons. They come off the negative terminal of the battery. The conventional current would actually go the opposite direction, would go clockwise, if you thought of positive charges. But notice it seems like we're getting an asymptote here. And notice that the voltage across the inductor is getting less, and then the voltage across the resistor is getting larger. And notice what is going on. Now that we're very close to a constant voltage across the resistor, the voltage across the inductor is getting very, very small. And notice that we're approaching a nearly constant current value. Let's take a look at this one more time. So this time the only change is I've zoomed further in on the voltage across the resistor. I've zoomed further in on the current in the circuit here, so we can see the change in the graph a little better. And notice that, let's think about what's going on before we close the switch again. Notice that when we first close the switch, there's a huge change in voltage in the circuit, and the inductor pushes back against the electrons very hard, because when we have a changing electric field, that is a changing current in time, the inductor pushes back with a large change in its magnetic field. And we don't allow the charge to move across as quickly as it otherwise sort of would like to if there was only a single resistor. Hopefully you noticed the final current was 1.20 amperes. That's because 12.0 volts divided by 10.00 ohms should be 1.20 amperes. That just follows Ohm's law. But at the first moment we close the switch, the current is very small, but it builds up over time, and it builds up in terms of a logistic way. Well, not so much a logistic way. It turns out that, one of the things you see is that the current goes up as a function of time, and then it levels off. So let's go ahead and close the switch. So you see the current building up as a function of time, and the voltage across the resistor is building up as a function of time. But notice the voltage across the inductor is going down as a function of time. Look at this current right here. It's approaching 1.2 amperes. And notice that that's about the value we're going to level out at here. And the voltage here is approaching about 12 volts, which is what we expect because that's the voltage of the EMF source. Now, by the way, we call this a charging LR circuit. A charging LR circuit. What are we charging? Well, we're not really charging electric charge. We're putting energy in the magnetic field of the inductor. And the idea is that we're storing up charge in that once we get to a constant current, and by the way, the constant current is going to be here when about we have very, very, very small, in fact, nearly zero voltage change across the inductor, we are going to have a bunch of energy stored in the magnetic field of the inductor. In fact, you may wonder, what did I do while I took that short break and made changes here? Well, what I did is I paused the simulation here. I went ahead and clicked Discharge Inductor, and then if I open the switch and let it run, you'll see there's a huge change in voltage there. In some sense, there's an enormous amount of energy built up on this inductor stored in its magnetic field. Okay? So this is what we mean by a charging LR circuit. You could also discharge, and in order to discharge, you do not have a battery here. So one thing we could do is we could charge this again. Of course, this will take a certain amount of time. Now, by the way, the time it takes to charge this inductor depends upon both the resistance and the inductance, okay? And, that is going to reflect the so-called time constant. But then, what you could do is you could remove the voltage source. So perhaps I pause here, I leave the inductor charged, I open the switch for a second, and then I remove the voltage source, I reconnect the switch, and then now I allow this inductor to discharge. So now you see that the voltage across the resistor is exponentially decaying, and then the voltage across the inductor is changing its sign in terms of its voltage, okay? But it's also decaying as a function of time. And the current in the circuit is definitely also decaying as a function of time if you discharge the inductor, okay? So that's a discharging LR circuit. So now let's look at an LR circuit in some more detail. What I have here is I have a resistor and an inductor, and I have a switch and then an EMF source. Let's assume ideal wires, ideal battery, and the voltage is set to 10 volts of the battery, and I can change the resistance or the inductance. And notice that it will calculate for me what the time constant is and the current. So this is going to be a charging LR circuit. That is to say, when we close the switch, we're going to see that the current should asymptote as a function of time. So let's go ahead and examine this. Okay, notice that the final current we reach is going to be the EMF divided by the resistance, because that's just given by Ohm's law. Notice the current, the conventional current, that is, comes off the positive terminal of this battery and goes around clockwise in this way. All right, and one of the things you also see is that the time constant is when we reach 0.632, that is 1 over E. It's actually 1 minus 1 over E, and in lowercase e there being Euler's number, the natural exponential. So we've reached 1 minus 1 over E fraction of the maximum current. Again, this time constant is often thought of as sort of the characteristic time, or the E folding time, you might say. So notice the current ends up being about 6.65 milliamperes, and I think that's because we have 10 volts divided by 1,500 ohms. Okay, so again, that's going to be 0.665. Okay, so actually very close to 2/3 of an ampere. Okay, so that's the idea. Now let's see if we reset, and let's see what happens if we increase the resistance. Notice it looks like the time constant goes down, and let's think about why that is. So if we have greater resistance, I think it should take less time for this current to reach its maximum value. Why is that? Well, because of Ohm's law, if you have a greater resistance, the maximum value of the current you need to reach is smaller. So it doesn't take as long to get there. So when we close the switch, we see the time constant is shorter, and indeed, the EMF divided by R is indeed less. And then we only have 5 milliamperes. So 5 times 10 to the minus 3 amperes. Because again, 10 volts divided by 2,000 ohms, we get that value. All right, how about if we go back to our original value of resistance, but now let's increase the inductance. Notice the time constant is larger. Let's think about why that is. So if we have a larger inductance, the inductor pushes back against the battery more with a stronger push. And let's think about why that is. An inductor likes to build up energy in its magnetic field. So if it has a larger inductance, when the battery pushes on the inductor pushes back even harder, and it takes a long time for that current to build up. So let's go ahead and see what happens when we do that. So notice, indeed, it's taking a long time to build up to that current value that we were seeking of 6.667 milliamperes. Because again, it's 10 volts divided by 1,500 ohms. Notice the inductance is 2.0 henries. How do we get 1.33 milliseconds? Well, we take the inductance L, we divide by the resistance R, and we get the time constant. And notice that because this is in henries and this is in kiloohms, the time is in milliseconds. Okay, and then how about if both are larger? Well, notice that we get back to that same time constant. But in other words, we're going to build up to a higher current than the first experiment, but we're also going to, so you would think that would take longer, but then we're also pushing back on the inductor, so that actually it should take the same amount of time in terms of the time constant of the first experiment. So let's go ahead and do that. Okay, so the time constant is back to 1.0 milliseconds. Okay, so you get the idea that it takes less time, you might say, if you have a greater resistance, but it takes more time, you might say, if you have a greater inductance. Let's go ahead and see this for a discharging LR circuit. So what I have shown here is a discharging LR circuit. That is, we're going to throw this switch from position A to position B. Position A, we charge the inductor. Position B, we're going to allow the inductor to discharge. Again, the resistance and the inductance are set at 1.5 kiloohms and 1.5 henries. Remember, henries is the units of inductance. And the time constant should be 1.0 milliseconds. But notice I think we're going to have exponential decay. Because we don't have any voltage source, the inductor is just going to dissipate its energy through the resistor. Now, we don't really want to say it dissipates its charge per se. An inductor does not store charge. An inductor stores energy in its magnetic field. So let's go ahead and flip the switch from A to B. And notice that we have this exponential decay of electric current. And notice that 0.368 is associated with the time constant, because 0.368 is 36.8%, and that's 1 over E. And E is Euler's number, the natural exponential. So the time constant is the time it takes for us to get to 1 over E of the original electric current value. So again, tau is often called the time constant, or the characteristic time, or the E-folding time of this circuit. Well, what's going to happen if we increase the resistance? Well, if we increase the resistance, the time constant should be less. Let's think about why that is. Because if you have a greater resistance, then the current is not as large, or at least you might say the resistor is so large that the current gets dissipated very quickly. And so when we flip the switch from A to B, we dissipate even more quickly than we did the first time round. Okay? Now, let's also do the reverse like we did before and change the inductance to a larger inductance. And then notice that when we flip the switch from A to B, the inductor is going to push back harder. So I think it's going to take more time to discharge than the first experiment. And that is indeed what we see. Because as soon as current starts changing, the inductor starts pushing back because it has energy stored in its magnetic field. The inductor works on Faraday's law. As quickly as the current changes in time, that gives a voltage pushback, if you will, by the inductor. Now, let's go ahead and see if we increase them both. So we get back to the time constant we had before. So you might think it should go faster because we have a greater resistance, but because we have a larger inductance, it actually sort of evens out to like the original experiment, and that is what we see. Okay, so this is exponential decay of an LR circuit, inductor and a resistor. This is not too extremely different than a RC circuit, a resistor and a capacitor circuit that we've seen before earlier in this course. But the energy is stored in the magnetic field, not in the electric field. It's stored in the fact that current changes across the inductor. It's not stored in the fact that there's charge between the plates of a capacitor. But notice that there's still that logistic growth, and then we also have this exponential decay. Now what I have shown here is a different type of circuit. something we haven't seen before. And that's going to be a LC circuit. That is an inductor and a capacitor circuit. Okay? Now, by the way, what we're going to do is in this LC circuit, we're going to charge things up, and then we are going to remove the battery and see what interesting effects we have. Okay? So, what we're going to do is we're going to store energy in this inductor and this capacitor, and then when we remove the battery, we'll see how those two interact with each other. So what I'm showing here is the schematic diagram with the wires and with the battery right here, the EMF source that's constant, a switch, the capacitor, and the inductor. Remember, capacitor is in farads, and then inductance is in henries. In fact, I can even show the values here. Okay, so we've got a 0.1 farad capacitor, a 50 henry inductor, and then a 12 volt battery. And we also have a current meter, an ammeter, which is shown here. So everything's in series, so the current should be the same all the way throughout the circuit. We're measuring the voltage across this inductor, and we're also measuring the voltage across this capacitor. In fact, I'll go ahead and measure the voltage across this capacitor also like so, because I think that the idea is that we'll see some interesting effects here. Okay, but what I want to do to make this a little more intuitive or realistic is I'll use the lifelike version, where we can see this copper wire and what these devices look like sort of in real life when you build them on a laboratory bench. And what we're also going to do is we're going to allow us to see the electrons. So remember, these electrons are pictorial, these are simulated, but again, it gives you a more intuition about what's going on with this circuit. So it's hard to say what's going to go on. So why don't we close the switch and see what happens? And let's go play. Okay, so notice that it looks like the voltage across this inductor started off at a very large value, and then it quickly dissipated. Look at the voltage across the capacitor. Notice that it went up, and now it's coming back down. And then notice that it's going to go back up again. So let's think about what's going on. The battery has a positive polarity connected to this side of the voltmeter. Notice the negative side of the battery is connected to the negative side of the capacitor here. But notice, at a moment like right now, there's a large voltage across the inductor. That's because, I don't know if you just noticed, but the current changed direction. Notice that the current is a time-varying function. You can see that here. But then the voltage is a time-varying function on both the inductor and the capacitor. Okay? Let's in fact pause it when it gets near one of those maximum points and see if we can understand what's going on. So right around here, notice that right around here, it looks like the current has changed direction all of a sudden. Notice that the capacitor was really charged, and notice that now the capacitor is going to start pushing charge out. Okay? And notice that the inductor, depending upon how the current changes, that's going to change what's going on in the inductor. So notice the current is reaching its maximum value again. The capacitor is charged. And look at the inductor. The inductor is changing most rapidly. Notice now the current is going back down. And let's go right around here. Why is the inductor at its largest voltage right now? Well, because I think the current is changing most rapidly. Notice at this exact moment, listen to me, the capacitor is uncharged. And now the current starts to go still the other way. But notice that, again, this ammeter is just measuring the magnitude of the current. The actual current, if it's positive or negative, is being measured down here. And we can see it's varying as a sinusoidal wave. So notice that as the current pushes back in the opposite direction, again, the inductor changes its polarity, as does the capacitor here. Now notice the capacitor is getting charged again. But then once the capacitor is sort of fully charged, look at this. The current's going to slow down to 0, and then it's going to start pushing back the opposite direction. In fact, if we wait for the capacitor to be fully charged again, which we'll wait for here in just a moment, and we pause, and then we remove the battery, we'll see kind of an interesting effect right here. Okay, so let's let the capacitor get fully charged. Right around there, approximately. Okay, notice it's right around 24 volts. Okay, remember the voltage source here is 12 volts. Okay, so we're going to take the voltmeter off the capacitor here for a second. Now, by the way, why 24 volts? Well, you could imagine we have two devices here, but all the energy is stored in the electric field on the capacitor. No energy right now is stored in the magnetic field. When the capacitor is discharged, all the energy is in the magnetic field, but it keeps reversing. So let's go ahead and remove the voltage source here, that is the battery. So I need to split this junction. I need to remove this battery. And let me go ahead and reconnect the wires. Let me measure the voltage across the capacitor again. And then 3, 2, 1. Let's go. So look at what's going on here. Notice we suddenly have a change. We suddenly have the voltage is still varying as a function of time, but look at this. Look what's happening to the inductor. The inductor is having a larger voltage variation, the same magnitude voltage variation as the capacitor was. And that's because these two are exactly out of phase from each other. Do you see that around time? Let's wait for it here. Right around time of 700 seconds, the capacitor has its smallest voltage across it, but the inductor has its maximum voltage across it. Notice that what we're going to do is we're just going to keep letting the current go back and forth like a spring. In other words, we're going to keep things time varying. Look at the current here. The current is also time varying. It's a sinusoidal oscillating wave. Okay, so let's go ahead and pause and let's be a little more quantitative with this, or at least like a simulation where we have a little more control, or at least like we can see things a little more directly. So what I have shown here is the similar situation to what we just had after we removed that battery. We have a capacitor and we have an inductor, labeled C, labeled L, and we also have a switch. Let's assume the capacitor is fully charged at first. We set the inductance to about 1.5 henries and the capacitance to about 1.3 farads. We're also going to see that this is going to look very similar to a frictionless mass on a spring, and we're going to see how things vary like such. We're going to plot the charge as a function of time and the current as a function of time. That is the charge on the capacitor and the current across this circuit. Well, let's go ahead and see what happens. Notice it's very similar to simple harmonic motion for a spring oscillating. Notice that when the charge is at a minimum, that is negative on the top, positive on the bottom, notice that the current was 0 because we were fully charged. Notice also when the capacitor is completely uncharged, like right now. So right now when the capacitor was uncharged, notice that the inductor had its, the current was actually a maximum. Because when the capacitor was uncharged, the inductor had its maximum magnetic field, and the current was moving the most rapidly, at least changing the most rapidly. Okay? And notice that this is very similar to simple harmonic motion, because right now all the energy is stored in the capacitor. All the energy in the spring is stored in the elastic potential energy. Once we let this go, when the capacitor becomes uncharged, the current is the maximum in terms of magnitude when the charge is 0 on the capacitor. Notice when the current goes back to 0, the capacitor is charged again, but it's charged in the sense of the opposite polarity. When the charge in the capacitor goes back to 0, the current is at its maximum value, but again, a different direction, different polarity direction of the current. And then finally, when the capacitor is fully charged again, the charge is the maximum, but then the current is back to 0. So notice that these are two sinusoidal waves which are out of phase. This to me looks like a cosine wave. This to me looks like a negative sine wave. But wait a minute, we know that current is like the time derivative of the charge. And notice that the derivative of a cosine function is like a negative sine function. So that seems entirely reasonable. What should happen if we, let's say, increase the inductance, let's say? Well, if we increase the inductance, that's like increasing the mass on the spring constant. So it takes longer for this to happen. In other words, it's less frequent. Because if you have a greater mass on a spring, there's more inertia. Thus, if you have a greater inductance, you could imagine there's a slower time variation. By the way, we often call this an electromagnetic oscillating circuit. So, notice that it happens a lot more slowly. That is, it's a lot less frequent. Let's reset, and let's now go to, what if we increase the capacitance? Notice that's like having a smaller spring constant. Notice we're storing more energy in the capacitor, but it's now also going to take longer to discharge all that energy from the capacitor. So you see that the charge is a lot larger, so it takes a lot longer. The frequency is less often compared to the original experiment because, again, we're discharging a very large capacitance and a large amount of charge, you might say. Okay, and then what if L and C are both large? Well, the frequency is going to be less, the period is going to be very large. We're going to store a lot of energy in the capacitor, thus store a lot of energy in the magnetic field of the inductor. It's like having a small spring constant and a large mass. So it turns out that this thing is going to oscillate very slowly, relatively speaking. In other words, you have a lot of charge and you also have a lot of pushback from the inductor. So I hope this makes sense in terms of understanding inductors and understanding circuits that they're placed in. Previously we did LR circuits, inductors, resistors. Here we have LC circuits, inductors and capacitors. So I hope this is helpful to you, and I hope you understand the intuition of inductors in circuits. Please smash that like button if you enjoy this content. Please subscribe to the channel to grow the channel. Please share this amongst your social networks to those that will benefit. Thank you for watching High Peak Education, and I will see you in the next video.